and we have Yixiao Sheng here too, who has been doing most of this work. This work was also done in collaboration with these researchers here from Grenoble, and Yehuda Ben Zion from USC, as well as Frank Vernon and Dan Hollis from UC San Diego. And this work is mostly part of the FoldScan ERC project. So feel really free to interrupt and ask for comments, clarification during the presentation. Okay, so here the motivation of this work is to monitor the preparation phase of large earthquakes on real faults. So here, as an example, I took this nice figure from Camilla from her recent paper, showing that for her numerical simulations, this large rupture here was preceded by processes of interplay between creep and foreshocks, and that these happen to be extremely difficult to detect by standard geodetic seismic methods. And so the goal of the project here is to try to improve the detection of such processes occurring before large ruptures by using some techniques of measuring seismic velocity perturbations associated with these processes. So in practice, here we want to mimic what's done on in the lab on rock physics experiments, where people measure seismic velocity changes on a rock sample by emitting seismic sources or acoustic sources using piezoelectric sources and recording the signal transmitted through the rock sample using also piezoelectric receivers, and measuring the changes in travel time, in flag times between these two sources and receivers, and measuring how this travel time vary during the rock physics experiments. And I took an example here from Marco et al., who show that the rupture on some rock sample was systematically preceded by velocity decreases as a precursory signal for the rock sample rupture. So we want to transpose this type of experiment to the real Earth on real faults. So in that case, what's difficult is to find sources that generate powerful seismic energy that can travel through the Earth at depth and probe the seismic faults. So it's extremely difficult to use controlled sources for monitoring faults, especially over long times, many years and decades. So we use seismic interferometry that makes use of ambient seismic noise sources that are more or less permanently generated, either naturally, like seismic swell here, or anthropogenic sources like large freight trains here, traffic noise, or also eventually plants, factories also generating seismic noise. And so the principle here is to correlate long time series at two seismic receivers to extract features, coherent features associated with waves traveling from one sensor to another that carry information about the Earth structure and its temporal evolution. So we carried this type of analysis in the past, and especially in the case of the 2004 Parkville earthquake, where we apply this type of approach, seismic interferometry, using low frequency surface waves generated by the oceanic swell to the seismic network around the San Andreas Fault in the region of the Parkville earthquake. And we extracted, this is a results that have been modified by Scuderi et al. Results showing the changes of seismic velocities that occurred, the drop of seismic velocity that occurred at the time of the Parkville earthquake, and showing also a very long-term recovery over many years. But in this specific example, we were not able to find some precursory activity, the precursory velocity changes. And some of the reasons we thought were that here the wavelength associated with microseismic noise were really high, about more than 10 kilometers. And also we used the coda waves extracted from the correlation of ambient seismic noise, which don't have a sharp sensitivity to the fault itself, but rather probe the volume around the fault. And so we wanted to improve this approach by, instead of working with the surface waves that have, again, a smooth, and coda wave that have a smooth sensitivity to fault zones, we wanted to carry an analysis where we would rather extract body waves from these noise correlations, stable body waves that will have an increased sensitivity within the core of the fault zones. So this is was quite challenging because most of the seismic interferometry work will extract surface wave for either tomography or monitoring purposes, but it found to be very difficult to extract body waves, probably because the lack of clear source of body waves. And we followed actually the pioneer work of Asaf Inbal in 2018, who showed that actually large freight trains in California, Southern California, could generate tremor that could be recorded as far as 70 kilometers from the railway. And here is a typical spectrogram for this type of very large freight trains. And they show powerful energy around 5 hertz and typically last around 20 minutes for the longest of these trains that can be as long as 5 kilometers long, for example. Also, here in this paper from Laura Pinson-Rincon, we identified all the possible freight trains that could generate powerful seismic sources that could be used to extract especially body waves at long distances. That's for the entire US. And we focus on this area here in Southern California of the San Jacinto Fault. So we started to work in the San Jacinto Fault in Southern California because of the very high seismicity on that fault. This is the LA Basin here, the Salton Sea, and the San Andreas running here on the east, and the San Jacinto Fault here. So it gathers about 10% of the total seismicity of Southern California. And there's a large earthquake, which is expected in this region too. And also, that's the location where Inbal et al. They found these large freight trains running here in this region of the Coachella Valley that radiates seismic energy within the San Jacinto fault area. Also because it's a very densely instrumented area with a large number of permanent stations that have been recording ambient seismic noise for a decade or more. So in 2018, we performed a first pilot experiment where we deployed 400 seismic stations to test this idea of extracting body waves, specifically P wave, crossing the San Jacinto fault in conditions similar to what we could have for, again, rock physics experiments. So we deployed 400 seismic stations on one side of the fault and 100 seismic stations on the other side. And we, here are the type of stations that we used. In this case, we only had 20 days of continuous data acquisition due to the lifetime of the batteries that we used here. And for this application, we then correlated between the two arrays. We correlated the train tremors. So we first detected the train tremor using permanent stations nearby the Coachella Valley. Here, again, as an example of the records for the permanent station close to the railways. And we then correlated between the two arrays the time corresponding to these train tremors with energy traveling through the San Jacinto fault again. And this is the result shown here on this panel. We have the distance. So the distance is, again, the distance between all pairs of seismic sensors between the two arrays that we correlated together for the train tremors. And the time lag here is the timeline of the train correlation with positive time lag corresponding here to energy traveling from the east, so from the Coachella Valley, to the west, to the San Jacinto fault. And what we found after this correlation process of the 20 days of train tremors, we have about 10 to 15 train tremor correlated per day. We found a very clear body wave here in the correlation with an apparent velocity of 6 kilometers per second, dominant frequency of about 5 hertz, corresponding then to a wavelength of about 1 kilometer. So again, have to keep this number in mind compared to the long wavelength of 10 kilometers or more that we use for surface wave when we correlated microseismic noise surface wave from the ocean. Here, wavelength is much shorter, and we are not using here, in this case, coda waves, so late arrivals, but ballistic P wave. We use ballistic P wave that for which we can actually model the sensitivity in terms of velocity perturbation at depth quite well, because it's again its travel path is ballistic, so it's easier to model compared to coda waves. And so then finally we use this result as a kind of characterization of this P wave traveling between the two sides of the San Jacinto fault that we could extract by correlation approach. We finally use these to explore the correlation of data from the permanent stations along the San Jacinto fault. So going back then to a decade or more, correlating all the data, permanent data we had to identify and to monitor the fault zone activity there in the San Jacinto fault. And this is the work from Yixiao. We'll present you now.
All right, thanks, Florent. So I guess that's the cue for me to jump in. So here I'm going to introduce the detailed work that we did for the SCAN project. like Florent mentioned, that we try to use the seismic tremor generated by freight trains to extract body wave between between permanent seismic stations, and then use that to monitor the sound signal fault activities. So in order to use the train tremors, we need to identify them, and we weren't be able to get the schedule from the local operational company, so we have to do that in a seismological way. So we take one station, which is IDO here on the map, the top right corner of the map, and we use that as a reference to time when the train is passing by the study area. And so we did that in a rather simple way. So the steps are showing on the left-hand side. So we first take the raw seismic data. Here is 1 day's data, and then we did a bandpass filter between 3 to 5 hertz. That's the frequency range when the seismic signal is most energetic on the Pinon flats. And then on the figure, we can see some spikes. These are from trains, and also there are some larger spikes which last shorter. Those are local earthquakes. And then we further take an envelope of the time series, and then we smooth it for 2 minutes here. And the smoothing can suppress the short duration local earthquake signals. And then we take the peak from the smoothed envelope, and the peak is the time that we assume the train is passing by station IDO and also passing by the study area. And note that we exclude the study in the local daytime. So it's the gray color here on the figure. That's when so IDO is close to a road. So during the local time, there are some very strong traffic noise that will contaminate the signals. So we only focus on the nighttime here. And once we identify when the train is passing by the area, we take a 12 minutes time window and basically surrounding the peak. And then you perform cross correlation among stations close to the fault within that 12-minute time window. And then yeah.
It's Chris, sorry to interrupt, but yeah, it sounds just curious now. So, I have a picture of the train and the station, and if the train is several kilometers long, what does it correspond to? The first car of the train arriving near the station, or because presumably you feel the signals even when the train is still a few kilometers away from you, right?
Well, yeah, the peak is when the train is closest, or the heaviest part of the train is closest to station IDO. So we use the peak. We assume the peak is the time that the most energetic part of the train is passing by the study area. And then we take the
center of the train or something.
Yeah, then we take 12 minutes window surrounding that time and perform cross correlation.
Okay, thank you.
Yeah, and yeah, so here are some figures showing the cross correlation function. As Florent mentioned earlier, that at the beginning we try to perform cross correlation between arrays, because for arrays we can do distance bin stacking to enhance the signal to noise ratio, but arrays are only for a short period, so we cannot use that for long-term monitoring purpose. So the idea is really try to do station-to-station cross correlations. And here, the black colors show the array-to-station cross correlation. It's like a intermediate step between those two. And here we also use the distance bin stacking to enhance the signal-to-noise ratio. And we have 3 different panels that shows the results from array, which is shown here, to FRD and to PMD, and then to BO82A. And we can see we have very nice move out from array to station cross correlations. And then on top of that, we show the station to station cross correlation in red. So also from station IIPFO, so it's the borehole station sitting inside of the array to the other 3 stations. And one important thing that we would like to highlight here is array is very useful for phase identification. Because if you look at the middle panel, IPFO to PMD, if you just look at the red curve, it's really hard to see which phase it is, because we want to use P wave here, and the waveform is very complicated. But with the help of the array, we can identify the move out, and then P wave is here, and then following is the S wave, and then the surface wave. Right, so array is useful in this sense, even though they are only available for 20 days in this case. And then once we construct cross-correlation function, we confirm that they are very consistent with the array to station correlation functions. Then we can move on to perform long-term seismic velocity monitoring. So what we did here is we have some quality control on the correlation functions, and then we stack them over 1 month and then smooth it for about 2 months period. And then we identify the P phase and then calculate the travel time difference focusing on the P wave. And we use the wavelet method developed by Mao et al. to extract the travel time difference. And the red here is for an example showing for station pair I, PF4, and FRD. And the red shows the travel time difference measurement, and the blue shows the wavelet coherence. In general, the wavelet coherence is super high. And so note that we do not observe a periodic velocity change pattern as we normally would expect to see from surface wave cross-correlation from microseism. And rather, we see a very intriguing curious increasing of time shift happening around the beginning of 2014, lasted about 2 months. All right, and then so that is for one station pair, and we can repeat the process for many other station pairs in the study area. And on the left-hand side, we show also for many other stations, we see the same increasing time shift, more or less at the same time at the beginning of 2014, and that corresponds to the increase of dt corresponds to the velocity decrease. And on the right-hand side, even though it's not that clear compared to the positive time shift, but we see some negative time shift on many other station pairs in the region, right? And then we can we can do a sort of map view of the time shift, and red color shows the positive time shift, and corresponding to velocity drop again, and the blue color shows the negative time shift corresponding to velocity increase, and they fall into nicely in 2 different regions. And then you may ask, what if there's something happened to the railway or to the train that may also trigger some apparent time shift that we would observe? So we look at one station pair IDO and BEL. So those 2 stations are on the other side of the railway and far away from the San Jacinto fault. And you may remember that IDO is the station that we used as a reference to time the train. So essentially, if something happened to the railway or the train, and we would expect to see a velocity change or time shift measurement showing up on that station pair. And the result for that station pair is shown here in black color, and we do not see a very clear time shift on that. So that gives us some confidence that the velocity, the travel time difference that we observe is potentially triggered by some velocity change happened more close to the San Jacinto fault. All right, so then we have to come up with a way to explain what we observe, and know that we are using body wave, so they are less sensitive to the shallower part, to either due to a temperature change or pressure change, or groundwater level change. And also another interesting point is when we have a complicated spatial pattern showing velocity both increase and decrease happening more or less at the same time. And so we come up with an explanation that the velocity change is due to some volumetric strain perturbation, and potentially due to an aseismic slip, because there was no big rupture or a big earthquake happening during that time period. So we try to model that and to see if the modeling can help us explain the data. And so we start from a slip model, and then we simulate the volumetric strain perturbation from that using the column software. And then we translate the strain perturbation to velocity change. And we use a very empirical model that based on the observational data from multiple regions. And that stress velocity sensitivity decays exponentially along with steps. And then once we translate the strain perturbation to velocity change, we perform fully formed simulation of correlation functions, body wave correlation functions, and then try to measure the travel time difference. and then compare that with the observation we have, then update the slip model. So here event is the model, one possible model that we found that can explain the observation reasonably well. I'm not saying that it's the best model that we can do, but it's one possible model that can fit the data. And the black stick line here is the surface projection of the slip patch that we modeled. And the slip patch is about 4 kilometers long at the depths around 7 kilometers. And the amount of slip is about 0.2 meter. And the black triangle here shows the modeled travel time difference. And they match reasonably well with the observation, both in terms of the amplitude, but also in terms of the polarity, the sign. And the location of this slip patch is on the edge of the seismic gap, endoseismic gap. It's pretty close to the trifurcation region, and the depth is slightly shallower than the geodetic looking depth, which is marked by the magenta color here. So it's basically on the edge of the locked segment of the San Jacinto fault. So we have more slides on this interpretation, but I'll speak if you are interested. You can ask me about that later. So we, of course, it's not just one. It's just one possible explanation that we come up with. We cannot really rule out other possible explanations. But if you have some ideas, feel free to let us know. And so we want to continue our monitoring study here in the endoseismic gap. And you may note that we perform a month-long stacking, and then so we do not have a very sharp time resolution. So we try to see maybe by deploying a dense array, we can have a better sense of, well, the location of the trains, and then that may help us improve the time resolution of cross collisions. And then the idea is to perform a long-term seismic monitoring of this study area. So we deployed a dense array on the Pinon Flats at the April of earlier this year. And a team of us are going to go there this weekend, and they're going to swap the battery, and then the idea is to last 2 years, and maybe even more than that. And then we will upload the data to ARIS later, so that we can all analyze that. So that is for this the array. And so when I was doing the talk several times and other occasions, and I was suggested that maybe we should look at the tidal effects, so that can help us better understand the sensitivity between velocity and the strain. And so that's something that we are working on right now. And so what I'm showing here is really the areal strain, a simulation of the areal strain, which is the sum of the two horizontal components of the strain component. And then we try to identify the phase or the time period that we have, mostly extension and compression time period. And then we try to find the trains within those time period and then perform cross collisions and then measure the relative time difference. So here are some very preliminary results, and we try to update that later that we are working on. And so the first panel here shows the comparison between extension and compression. So we are using cross collisions from Pinon Flats to FRD here. And we use the data from 2015 to 2020. So we have some very wild distributions, and the fluctuations can be explained either due to the location of the trains is not super accurate. So there are some source effect, or some other potential trigger to the velocity perturbation. So we have some fluctuations here. However, the different centers around some negative value, which is about -2 milliseconds. So note that the DT here is calculated by extension minus compression, which is a little bit counterintuitive. And for the comparison, the lower panel shows the results between extension minus extension period. So normally we would expect a zero zero time shift in this case, and which is what we observe here. So it's somehow suggests that what we observe in the first panel is maybe trustworthy. And as I mentioned earlier, it's a little bit counterintuitive because during compression, we would expect to see velocity increase and therefore a smaller travel time. Therefore, we would expect to see a positive extension minus compression. However, what we are observing here is a negative value. And so we are not the first one who observing a velocity drop due to during the compression phase. A study by Hillers et al. In 2014, I believe, they used the Pinot flat temporary arrays, and they look at cross correlations. They look at velocity change due to tidal effects on cross collision functions within an array on Pinot flats, and they also see negative velocity change. They also see a velocity drop during the compressive time phase, and they attribute that to the dilatancy effect. So maybe that's also something that happened here, but still we need to more work needs to be done to verify that. And if you have some ideas or comments on that, feel free to let us know. And so that is one study that we are working on. Another study is we are trying to look at another area which is in ridge crest region. The idea is trying to use anthropogenic seismic noise to potentially extract body wave to look at velocity change. And we are particularly interested in the velocity change before the onset of the big earthquake in 2019 July. And so we deployed a temporary nodal array close to CLC station CLC here. And basically that array is slightly to the north of the epicenter of the 2019 main shock. And we are analyzing the data currently, and here are some very preliminary results on the data that we have. And on the top left corner, it shows the spectrogram on station CLC, and I stacked that over a 3 month period to enhance some common features over that time period. And I mute the microseismic signal in this case just so that we can see the high frequency energy clearer. And we observe some bands of energies around either 5 Hertz or 10 Hertz. And the other 4 panels shows the beamforming results using the array that we deployed. And it's also the stacked results over 3 months. And we can see that there's a very strong energy pointing to the southwest of the array. And so the circles mark the velocity for 6 kilometers, 3 kilometers, and 1.5 kilometers per second. And so I have a blue star here that marks the azimuth of a mining facility to the southwest of the array, southeast of the array. And so maybe the signal that we are seeing is from that mining facility. And so, again, it's an ongoing work, and we are trying to see if the correlation function is consistent comparing to now and also back to 2019, because the idea is really try to go back to 2019 to look at the velocity change. And so stay tuned. We are working on this as well. And so that's pretty much what we have for today, I think. And if you guys have any comments or questions, feel free to let us know.
All right, thanks so much. I will invite people to turn their camera on and their microphone and join me in thanking these guys. Fabulous talk. Yeah, really interesting.